Okay, everybody, so what we're going to do is the assistance walkthrough for exercise number 7, black holes. Remember that before you watch this video and work on the exercise, you need to make sure that you watch the introduction video. That's important because in the introduction video, I go over some details to help you understand what we're going to actually do in this exercise. So again, make sure that you watch that. Don't forget that also the quiz that is coming up will include questions that come from the introduction. So make sure that you check that out. On the first page here, this is just all introductory material, so make sure that you read it over, and hopefully you'll have a basic understanding as to what we're going to accomplish. Gives you some details. Again, a lot of this was covered in the introductory video. Page 59 is more of the same. It's again going through the important background information to help you understand the nature of what we're going to accomplish. These are the two equations that we're going to use in this exercise. And in the introduction video, what I did is I walked you through the meaning of these equations. We'll come back and revisit them in just a minute. But the first steps are listed here on the bottom of page 59. The first one is that what we want to do is, in step number 1, is to calculate the orbital velocity for the space shuttle as it orbits around the Earth. And remember that the information that we're going to use is going to be used in this equation. This is the equation for orbital velocity. In the equation, the information that we need is the mass of the Earth. And the mass of the Earth is given to you in Appendix A, so make sure that you use your appendix to find that information, and you can find that information right here. And then, of course, what we need to do is we need to supply the value for R, and this actually comes from the paragraph here. You'll notice that it says that the space shuttle is orbiting at an altitude of 300 kilometers above the surface of the Earth. Now, this is actually a fairly tricky calculation. This is one where a lot of students will have trouble with it. And so what I'm going to do is I'm going to set it up for you. I want you, of course, to do the math, but I'm going to set it up to help you get to the point where you can get this accomplished. So let's go ahead and switch to that. Okay, so what I did is I just simply rewrote this equation. Remember that G is the value that is the gravitational constant, and remember that that number comes off of your appendix. M is the mass of the Earth. It's essentially the mass of the thing that you're orbiting around. R is the distance from the center of the Earth to the object's center that's going around the Earth. So if it's the space shuttle orbiting around the Earth, R is going to be the distance from the center of the Earth to the center of the space shuttle. So that's what the value of R is. Now, here's what makes this kind of complicated. A couple of things. The first thing is, in this exercise, what we did was we gave you two pieces of information, and we want you to do a little bit of critical thinking. So R is this entire distance here. But in the exercise, the two parts that we gave you is that the first component is this part, and that's just the radius of the Earth. Okay? And then the second portion, see if I can draw it. It's a little bit tight here. But that is how far above the Earth the space shuttle is. I'm going to put an RS. So this little piece plus this piece together makes up what the value of R is. So R in the equation is actually the radius of the Earth plus the altitude of the space shuttle. So it's this piece plus this piece. Now, in the exercise, if you read the instructions, we tell you that the space shuttle is orbiting at an altitude of 300 kilometers above the surface of the Earth. So what we know is that RS is 300 kilometers. RE is the radius of the Earth, and remember that you find that using your appendix. There it is there, radius of the Earth. So 6,378, or 6.378 times 10 to the third kilometers. So this is 6.378 times 10 to the third kilometers. That's what that is. I'm going to put a parentheses around it, plus, and remember, this is 300 kilometers. So this is 300 kilometers. Okay. Now, the tricky part of this, well, first of all, that's kind of complicated, so make sure you fully understand that. That's what the value of r is. It's the combination of these two. But what makes this a little bit tricky for students is that for this equation to work properly using the value for g, you'll notice there's a note in the paragraph saying that the altitude of the shuttle and the radius of the Earth must be in meters. That's really important, and it's just simply because of the units that are used for the value of g, so it has to be in meters. And so what we need to do is we need to convert these two numbers into meters before we ever use the equation. Now there's a couple ways to look at this. One way is to just understand that it's powers of 10, and so what we're going to do is we have to multiply each number by 1,000. And the reason for that is because kilo means 1,000, so a kilometer means 1,000 meters. So every one of these kilometers has 1,000 meters in it. So it's this many kilometers times 1,000 turns it into meters. This many kilometers times 1,000. So 6.378 times 10 to the third times 1,000. Now, because these are powers of 10, you could, of course, please feel free to use your calculator. That's absolutely okay. But I'm just going to do a little bit of powers of 10. So this is going to end up being 6.378 times 10 to the 6 meters. So, and the reason why is because this is 3 decimal places and this turns this 3 into a 6. But again, please use your calculator if you're not sure how to do that. And remember, it turns it into meters. So this is, this is, get a little stab in my paper there. So this is the total number of meters that becomes. And then this is 300 times 1,000, which is 300,000. And I'm going to write it as powers of 10. It's going to be 10 to the 5th. And again, the reason why it's 10 to the 5th is because 300,000 is 10 to the 5th. So this many meters, and that's what r is altogether. So, excuse me, before you ever use this equation, we have to add these two together. And I'm going to use my calculator. So what you have is 6.378, and use the EE button, 6, EE6, plus 3, EE5, okay? So this is our answer. So it's going to be 6.678, and it's 1, 2, 3, 4, 5, 6 times 10 to the 6 meters. So this number is the r for this equation. Notice it's in meters, okay, and we've got the two combined together. So let's go ahead and rewrite the equation with some numbers in there. G is this number here, 6.673 times 10 to the minus 11. Don't forget it's minus 11. Don't worry about the units. I'm just going to leave them off. M is the mass of the Earth. There it is. Okay. 5.98 times 10 to the 24, and it's kilograms. Okay. Put a line. And then our R is this number here. Meters. And then this is the part a lot of people forget. It's the square root of all that. So square root, I'm going to draw a big old line here. There you go. So it's this number is G, this number is the mass of the Earth, got it off our appendix, and this is our correct version of the value for R, and it's in meters. And don't forget to take the square root. A lot of people forget to do that. Now, all you have to do at this point is to plug it into your calculator. A couple things. Make sure that you don't forget to use your EE button, 6.673 EE, negative 11, 5.98 EE, 24, so forth. And then don't forget to square root your answer. So remember, most calculators have a square root button to do that. Now, when you get your answer, it says that your answer will be in meters per second, meters per second. So what that means is that your answer is going to be something. Let's put a little squiggly box, but it's going to be in meters per second. And that answer goes in this box here. So the space shuttle's orbital velocity in meters per second. The next step is to convert that answer from meters per second into miles per hour. And the reason why we're doing that is because it'll just make more sense in your head if it's miles per hour. It's because that's the unit of speed that you're normally used to. So we have to convert meters per second into miles per hour. So let me show you how to do that. Once you have your answer in meters per second, the way that you do this is you have to turn meters into miles, and you have to turn seconds into hours. So miles per hour. So meters have to become miles, seconds have to become hours. And the way to do that is you need to have your appendix, and you need to notice that there is a connection between miles and meters. That's the first part. And then the connection between seconds to hours, we don't have on here so much because we hope that you can figure that out. And I'll show you how to do that in a second. So, but this is for sure the first thing you're going to do. So 1,610 meters are in every mile. So what you're going to do is you're going to take this answer and you're going to turn first meters into miles. And the way to do that is you're going to first divide it by 1610. Okay, and the reason why you're going to do that is because you have meters. I'll just write this out. Meters per second. I should just make it a singular, meters per second here. And so meters, so it's 1 mile per 1,610 meters. Okay, so I'm going to write it this way because we want meters to go away and we want the answer to be in miles. So notice that's essentially taking this answer and dividing it by 1,610. And then to get seconds into hours, remember there are 60 seconds in 1 minute. Okay, and there are 60 minutes in 1 hour. Okay, now notice what happens. Seconds will cancel, minutes will cancel, and notice the units that are not canceled, the ones that don't get canceled, are miles per hour, miles per hour. So it's divide by 1610, multiply by 60 twice. So this answer divided by 1,610 times 60 times 60. That answer will be in miles per hour. And let's put a squiggly because you get to do the math on that. So this is this answer converted into miles per hour. And remember that we want you to write that, oops, clunk. We want you to write that in this box here. Okay, so this is where you write this answer converted into miles per hour. Now, when you get these two answers, On Canvas, there is an answer checker that will help you verify these answers. There's a whole bunch of answers you get to verify in this exercise because it's kind of complicated. But before you go any further forward, make sure that this number is correct, and then make sure this number is correct. Because if this one's wrong, this one's definitely going to be wrong. So check this one, and then come back and do the work and check this one here. Okay, so the next step is going to be to explore the escape velocity for the Earth. Now we know from the work done here, we know what the orbital velocity is for the space shuttle. And by the way, it doesn't have to be the space shuttle. It could be anything orbiting the Earth, has to have that particular velocity. So it's independent of the body that's doing the orbiting. It has to do with where you are from the Earth and the Earth. Okay, so now what we want to do is to determine what is the velocity necessary to escape, to completely leave the Earth and go off to Mars or go off to somewhere else in the solar system or leave and go away forever. So we call that the escape velocity. You'll notice the equation looks almost the same, but it's not exactly the same. There is a difference. It is not only the difference of a 2, but it's a difference in what the value of r represents. So you'll notice that the value of r is just the radius of the thing that you're trying to escape from. So in this case, we're not going to worry about where you are or how far above the Earth you are. The idea is, imagine you're on the surface of the Earth and now you need to escape it by traveling at some particular speed or velocity to get away from the Earth. So r is always just the radius of the object that you're trying to escape. M is the mass of the object you're trying to escape. G is still G, and 2 is always 2. So it's a different looking equation, but it has a different meaning to it as well. So for question 3, there's 2 parts. It is very similar to what we did in step 2, I should say. So step 3 is to calculate the escape velocity for the Earth. And what I'm going to do is I'm going to show you how to do that. And then step 3b is to convert it to miles per hour, just like we did with step 2. So let me show you how to do 3a. I'm going to set it up for you. You obviously get to do the math, but let me go back to my paper here. Okay, so here's the equation. I just rewrote it on this piece of paper and have a diagram to go with it now. The value for G is still the same as before. M is still the mass of the Earth. That is not different. What's different is the r in this equation. So when it was the previous equation, when we were talking about something orbiting the Earth, r was a combination of 2 numbers. But in this case, this is easier. It's just the radius of the Earth. So r is just simply this. Okay. However, it still needs to be in meters. Okay, so it still has to be in the unit of meters. And so what we're going to do, I'll write it out and set it up. You get to do the math. So it's the square root of 2 and then G, M. But this is the radius of the Earth. All it is that. And again, it has to be in meters. So what we're going to do is I'll write it yet one more time, but this time we'll put in some numbers. So it's 2 and then G. Remember, get this from your appendix if you're not sure. And then M is the mass of the Earth, which was 5.98. 10 to the 24, and that's kilograms. And then this is the radius of the Earth. Let's explore that a little bit. Which is 6,378 kilometers. Okay, that's just right off the appendix. But remember, it has to be in meters. And if you remember from your previous step, we had to take this number, multiply it by 1,000 to get this number. So in meters, it's 6.378 times 10 to the 6. Okay, so remember, we're just going to take this number, multiply it by 1,000, and we get this number. So this is going to be 6,378 And don't forget, this is often the mistake that is made. It's the square root of all that. So here's the mistakes you want to avoid. Here are the two things that often happens. The first one is people in a hurry, they just simply stuff the previous value of r that you worked out on that other step. It's not the same value of r. It is just the radius of the Earth this time. So it is different. Don't use the one from step 2. And then the other mistake, of course, is that they forget that it's in meters. So make sure that you use the version of it in meters. And of course, don't forget to square root the answer. Now, when you do this, you're going to get some number, and remember, it's going to be in meters per second. That's just by design. So again, the way to get your answer from meters per second is to divide by 1610, then multiply by 60 twice. And that will give you the answer in miles per hour. Okay, so make sure you do that as well. Both of these answers are going to go in these two boxes, the escape velocity for the Earth in meters per second, and then the converted answer into miles per hour. And again, on Canvas, there's a way to check to make sure that these numbers are correct. So make sure that you go to the Canvas checker on that. The next step is there are a couple of questions. These are pretty self-explanatory. Read them carefully, think them through, make sure that you understand the question, and then of course you're going to write your answers in these two boxes here, question 1, question 2a. Okay, make sure you do that. Okay, so question number 4, what we're doing is we're going to calculate the escape velocity for the moon. We want to compare what is it like to or what speed, I should say, do you have to travel to leave the moon compared to the Earth? Is it harder to leave the moon? Is it easier to leave the moon if you're trying to escape? So we need to calculate that value. Now we're going to do it the exact same way that we did it in step 3. So if you recall, let me get my paperwork here. The only difference is that we need to use the same equation, but we need to substitute these two values because in this case we're going to have the moon. So what you need to do, excuse me, is you need to use the mass of the moon. And in the question, we give you the mass of the moon. There it is, 7.36 10 to the 22. So that's going to be your value for m. And then the r, the radius of the moon, is 1,737 kilometers. And again, don't forget it has to be in meters. So you're going to have to convert this into meters. And if you remember, you just multiply by 1,000. So the value of r is going to be for the moon in meters. And you just do the math exactly the same way. So this is going to be the same number. This will be the value for the moon in meters, and this will be the value for the moon. So make sure that you use those numbers. And when you get that answer, here's the part that a lot of students don't quite understand, is your answer is going to be in meters per second as it is supposed to be, but we want you to just simply go straight into converting it to miles per hour. So you're going to have to do this to it as well, because what you'll notice is we are just simply asking for the answer in miles per hour. So we're not going to have you write both numbers down. So just simply calculate it in meters per second and calculate it to convert it into miles per hour, and that's what you're going to write down. And again, on Canvas, there's a way to check this answer. Here's where question 2b comes in. So the idea is that let's pretend that you're going to shoot something off of the surface of the moon. One of the things that people actually thought about back in the early part of the 20th century is, could we build a cannon big enough to shoot something into space? You know, maybe it doesn't take a rocket, maybe just like pointing a gun up and you shoot a bullet. Does that bullet ever get into space? Can you shoot a cannon into space? So what we're going to do is we're going to find out that answer. And what we have here is basically a question saying that if we were to take some sort of a military style cannon and we were to shoot that cannon, the question is, with the escape velocity of the moon, is it possible to shoot an artillery shell into the air and have it leave the moon? So what you'll notice is that the question number 1 has part of our answer. So the fastest military shell, we actually looked this up on Google. So if you use a cannon in the military, the best that they have, this is the fastest speed that a military shell will travel, 4,100 miles per hour. So you're going to compare this number to your answer that you got for step 4. So in other words, is the answer for the escape velocity more or less than this? And that will help you determine, is this fast enough to shoot something off the surface of the moon? So could you have, let's say, a military base on the moon that's going to try to shoot at the Earth? Let's say the future moon people get mad at the Earth and they want to start shooting at us from the moon. Is it possible to shoot a military style shell from the surface of the moon to the Earth? So this is what we're going to explore in that one. I know it's kind of silly, but at least addresses that question. Now, question number 5 is what we want to do is the same procedure, but we want to do it by determining the escape velocity for the sun. Okay, so it is the same setup, but remember that in this version of the question, the m is going to be the mass of the sun, and the r is going to be the radius of the sun. Don't forget it has to be in meters. Now, where do you find that information? Your appendix will have the mass of the sun in kilograms, good to go on that, and it's going to have the radius of the sun, but it's in kilometers. You have to convert that to meters, so make sure that you do that. And then you're just going to use the same equation, and what you'll do is you'll determine the escape velocity for the sun. Remember, your answer is automatically in meters per second, so we want you to report it on your data sheet in miles per hour. So you have to make that conversion. And then what you're going to do is you're going to write those answers in these boxes here. So at this point, you should have a number for this, an answer for this, and now a number for this. Remember, Canvas is going to have a way for you to check these. So on Canvas, you can check this number. On Canvas, you can check this number. And then, of course, what we do next is answer a couple of questions. And so question 3A and 3B, what I want you to do is just to read it very carefully and then try to answer the question. The first one is saying is that what happens to the escape velocity if the object's mass doesn't change, if it keeps the same mass, but is going to get larger as time goes by. So I want you to kind of think about how that works. I'll give you a hint. Let's go to this equation here. What we're saying is this number stays the same, but this number gets bigger and bigger and bigger and bigger. So it's imagined that the Earth's size, not its mass, was growing. So what does this do if this number gets bigger and bigger and bigger? I'll give you a hint. This is in the bottom. This is in the top. And so these are inversely proportional to each other. So when this gets bigger, you need to figure out what this is going to do. Question number 3B is pretty much the same idea, but it's the reverse. We want you to explore what would happen if the object stayed the same in its mass, but the size of the object got physically smaller. Okay, so the next step is to continue reading through the instructions, a couple things for you to think about as you go through it. So the final part of the exercise is we're now going to explore in more detail the idea of the black hole at the center of the Milky Way galaxy. And so read the instructions, make sure you read them carefully. Step 6 is to use the information in Table A, and what you're going to do with that information is you're going to determine the information that's related to the black hole at the center of our galaxy. And so the way to do that is you need to graph this information, and we provide you with the graph paper in this week's exercise. Here it is here. And so what you need to do is you need to take, see if I can get both on there, it looks like I can. You need to take this information and graph it onto here. Now, a couple things to think about. The first one is that you need to set it up correctly. Notice it's X and Y, and remember by convention, the first number is X, the second number is Y. And what you need to do is you need to simply count the solid lines as whole numbers. So 1, 2, 3, 4, 5. It's negative because we're going that way. 1, 2, 3, 4, 5, positive, and then so forth. So negative 4.6, positive 9 is going to be negative 4.6, positive 9. So the dot will be somewhere up here. Now, when you make this graph, if you do this properly and you do all the coordinates the way they're supposed to, you should have an ellipse. It should look about like what I'm sort of mimicking here. There should be an ellipse that's about this big on your page. If it's little small one, you did it wrong. If it doesn't fit, you did it wrong. So again, if you do it correctly using whole numbers for the solid lines, it'll be about this big and it'll be shaped sort of like this on your page. In step 6, it says to, again, sketch a best fit curved line. So what that simply means is don't just do a jagged connect the dots. Just sort of smoothly draw the ellipse through those data points. Step 7 is what we want you to do is to identify and measure the size of the semi-major axis for the orbit of the star S2. Now, this is going to require you to remember what semi-major axis is. And so this is where a lot of students, just because they get in a hurry, especially you students who are working on this late on Friday night, give yourself time, don't do this late Friday night. But anyways, you need to do a little bit of research. So go back to page 47 in the lab manual because it's going to tell you what the semi-major axis is. This is really, really important. A lot of students I've seen in my years of teaching this class screw this up because they don't do this step. So go back to the page and remember what the semi-major axis is. I'll help you with that here. Okay, so here's page 47, and this is the picture that we're most interested in because the semi-major axis is that. So make sure that you look at your graph carefully and remember that it's the whole thing divided in two. So you're going to measure what this is. And the way to do that is on your page. I'm going to turn it because on yours it's going to look like this. On your graph it'll be like this. Take your ruler, measure the whole thing, and then divide by 2. And then when you do that, you'll have the semi-major axis. And you're going to report it in this box on the data table. So again, that's the semi-major axis. Measure it in millimeters. Make sure you're careful and you do it in millimeters, not centimeters. Now the next step is we want to know what the semi-major axis is in astronomical units. And the way to do that is to use this bar down here. So if you remember, page 11 is a tutorial. If you forget how to do that, you're going to measure the length of the bar in millimeters, set it equal to 350 AUs, and then what you want is the number of AUs per millimeter. Okay. And then what you'll do is when you measure the semi-major axis and you have that answer, what you're going to do with this number is you're going to multiply it by this number to turn it into astronomical units. So you'll have a way to check these two numbers on Canvas. So make sure that you have this measurement turned into astronomical units. Okay, so you now have, hopefully all the way through step 8, you have the answer to the semi-major axis measured and then converted into AUs. Now we're ready to determine the mass of the black hole at the center of the galaxy. And the way to do that is to use this equation here. Now this is easier than it looks. The D is the value we need to put in. The P is going to be given to you. So let's go through this. The P is in Earth years, and notice we're going to just give it to you in Earth years. So P is just 15.2. Don't forget to square it. And then D is the answer from the previous question in AUs. So what you're going to do is you're going to take this answer that you determined in this step here, and you're going to plug it into this number here. And don't forget to cube it. And then once you divide those two answers, you'll have the mass of the black hole at the center of the galaxy, and you're going to go ahead and write it in this box here. Now notice it says the unit is called solar masses. Here's what that means. If you use the equation the way that we've set it up, what it means is that your answer is comparable to the mass of the sun. So one solar mass, and this, by the way, is the way that it's abbreviated. So one solar mass is equal to the mass of the sun. So think of it as the number of atoms or all the material that the sun is made out of is simply called one solar mass. So this answer is going to be in units of solar masses. Now the reason why this is important is because in a future step you're going to need that answer to be in solar masses, but we'll get there in a moment. Step 10 is to simply determine or show on your graph where the center of the Milky Way is, or essentially the location of the black hole at the center of the Milky Way. So it says the center of the Milky Way galaxy is located at this coordinate position. So what you're going to do is you're going to take your graph and you're just simply going to write an X where that is. I'll give you a hint. It's going to be somewhere down here. So just simply put an X at the location, because we want you to see the orbit of the star S2, and we want you to see the center of the Milky Way, or the location of that black hole. So you can see the orbit of the star S2 around the black hole. Okay, so there's some stuff to read through. Make sure you read it carefully. And then again, we're going to talk a little bit more about what the event horizon is. If you watch the introductory video, this will make sense. But again, make sure that you read through that. Okay, so on our last page, 63, we're almost at we're sort of heading down the home stretch here. So what we want you to do is we want you to now determine some more information about the black hole at the center of the galaxy. And one of the things we're leading up to is what is the size of the event horizon of the black hole. If you watch the introductory video, this will make more sense to you, so make sure that you watch that. So what we're going to use is this equation. This is the equation from the introductory video that is the way that you determine the size of the event horizon. And if you watched that video, officially it is called the Schwarzschild radius. So that's why we're going to call it R sub S, S for Schwarzschild, R for radius. And this is the formula that calculates that. Now, to make this calculation happen, a couple of important things. The first one is that M is the mass of the black hole. And we'll come back to that in a minute. And C is the speed of light. But to make this equation work, we have to have them in the proper units. So step 11 is to take your mass of the Milky Way galaxy, mass of the black hole at the center of the galaxy, and we need to convert it from solar masses into kilograms. So in other words, we need this number to be in the number called kilograms, or the unit called kilograms. So you will have the answer in solar masses from your previous step. We want it to be the number reported in kilograms. And the way to do that is to remember that you have a conversion on here to make that happen. And so if you, let me see, go down here, you'll see here that the sun's mass is reported in kilograms. So what you simply need to do is you need to take this number that's in solar masses and convert it to kilograms. And the way that you do that is you multiply this number by this number. So this number times this number will give you the converted mass in kilograms. Okay, so it's a multiplication. And then again on Canvas, you can check all of these numbers to make sure that they're right. So at this point, we're ready to determine the size of the event horizon for the black hole at the center of the Milky Way. So we're ready to use this equation. What you're going to do is you're going to supply the value for M. Remember that if you do this correctly, let me get my paper out. So remember, what you're going to do is M is going to be a number that has to be in kilograms. So M is going to be this number. And then C is a constant. It's the speed of light. And the way that you find that is you simply find it here. So this is the speed of light that we represent it with the symbol C, but it's in kilometers per second. So the problem is this has to be meters per second. So what you have to do is you need to take the number from the appendix, this number, and you need to convert it into meters per second. And let me show you how to do that. I'm going to actually write it up here. So 2.99 times 10 to the 5th kilometers per second is the number from the appendix. And then remember, every kilometer has 1,000 meters. So you're going to multiply this by 1,000. So the speed of light is going to be 2.99 times 10 to the 8 meters per second. So that's just simply 1,000 times this number. So this number here is the number that goes in for C. However, many students forget that it has to be squared. So this number squared is what the bottom is. This number squared goes in the bottom. This number is this number. G is still G. Look it up on your appendix. 2 is still 2. No square root for the whole thing. So 2 times G times this number divided by this number squared. A lot of people have trouble with this number and this calculation, so make sure that you listen and follow this carefully. And of course, when you get the answer, you're going to report it right here. It is automatically in meters because this is in meters. And then on Canvas, there's a way to check this answer. Step 13 is to simply take your answer from step 12 and convert it from meters to miles. And the reason why we do that is because you and I think of things more in non-metric units. So miles is going to make more sense to us. So what you're going to do is take this number and you're going to convert it into miles. And remember that you can do this by using this number here. Okay, so remember that it's 1610 meters in every mile. So make sure you use that conversion to get this into miles. Step number 14 is, and 15 to be honest with you, I guess 16 too, is we're just going to have a little bit of fun with the idea. So what we're going to do is we're going to repeat this exact same thing, but we're going to use the sun. So in other words, what if the sun were to turn into a black hole? Now, I'll tell you, the sun cannot turn into a black hole. There's a variety of reasons why it can't. It's not the right mass. Gravity is not powerful enough to make the sun into a black hole. But let's just pretend that the sun did turn into a black hole for some reason. So the question is, how big would the event horizon be for the sun if that were to happen? So you're going to just use this equation again. Now here's the difference though. The m in this equation is going to simply be the mass of the sun. So m is simply going to be that number. And then the 2 is still 2, G is still G, and then again it's this number on the bottom. Make sure you square it, this number squared on the bottom. Mass of the sun, this number squared, 2 times G. And then do all the math on that. Again, step 15, the Earth is not going to turn into a black hole. But let's say that something happened and it made the Earth into a black hole. How big would the event horizon be if the Earth had turned into a black hole? Same thing. The difference this time is m is going to be the mass of the Earth. And we have the mass of the Earth right there. So that's going to be your m. C squared is still this number squared. So make sure you square it. This number squared. Make sure you use the converted one. Do the math. And when you do the math, you report your answer here. Okay. And then the final one is, what if you, let's say something happened, a terrible accident in a laboratory, and you were turned into a black hole. Now, here's the cool thing, I think. It is physically possible to have something turn you into a black hole. And the reason is anything in the universe can become a black hole. The reason why that is because this equation simply tells us that if you make something sufficiently small enough, then its own self-gravity will turn that object into a black hole. So this pencil can be turned into a black hole. Why? It has mass. You have mass. The sun has mass. The Earth has mass. So you could physically be turned into a black hole if something were to shrink you small enough to make that happen. So this is basically saying how small something has to be for it to be a black hole. Now, there's no real chance that anything in the universe is going to do that to you or to the Earth or to the sun for that matter. So, but let's just play with it. What would be the size of your event horizon? How small would you have to be crushed down to, your body and its mass crushed down, to become a black hole? So we can calculate that. The reason is because you have mass, and we can simply just plug it right into this equation. But it has to be your mass in kilograms. So what we're going to do is, what you need to do is take your body weight. Just think about what your body weight is if you were to step on a scale. For instance, I step on a scale every now and then, so I know what my body weight is. And then take your weight in pounds, and you're going to turn it into kilograms. And the way that you do that is there are 2.2 pounds in every kilogram. So you're going to take your body weight and you're going to divide it by 2.2. And when you do that, you take that number and you plug it in for the value for m. So it's your body weight divided by 2.2. That's the number for m. C squared is still c squared. Remember, it's this version of c squared. And then plug it in, do the math, and that number will be how big your event horizon would be if you were turned into a black hole. And so you're going to put that number in this box here. Now, I'll give you a hint. It's going to be a very, very, very small number. So it's going to be some number times 10 to a very big negative number. So it'll be a very big negative exponent up here because it's a very tiny, tiny number. It's way smaller than the size of a proton. It is smaller than almost anything in the universe because obviously you don't have a lot of mass. And so the ability for your small amount of mass to be turned into a black hole means you have to shrink a whole lot. You got to get really, 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 really tiny before your mass can ever become a black hole. So the number is going to be a very, very small number. Okay, so again, make sure that you have your numbers written in here. Make sure that your name is included on the data sheet. What you're going to turn in to me this week are two things. First of all, you need to turn in your data sheet with all of your answers. Remember, on Canvas, you can check most of these answers. And then you need to turn in your graph. So there's two things that you're going to take pictures of to include. And again, make sure that your graph is included and turn that in through Canvas and make sure that you turn it in by the deadline. If you have any questions at all, again, feel free to contact me through Canvas or email. So let me remind you once again that it's important that you try to get these exercises done early enough in the week, because if you have trouble with the exercise, I can look at what you've uploaded. I can try to give you advice and give you a chance to fix your mistakes. This exercise in particular is a complicated one. A lot of people have trouble with it. So again, make sure that you get it done as early as possible so that you can submit it in time for me to check it, and you can get that notification that it needs to be fixed and that you can spend the time to fix it, and you can upload it before the deadline. So that's kind of important as well. Otherwise, good luck.